We will now study integrals involving inverse trigonometric functions. We're not going to be integrating inverse trigonometric functions, but we will examine the integrals of algebraic functions that yield inverse trigonometric functions. Now, if you'll remember, one video ago, we learned that there are 6 different formulas for differentiating our inverse trig functions. Let me remind you of one pair of those formulas. The derivative with respect to x of inverse sine of u is equal to u prime over the square root of 1 minus u squared. And very similarly, the derivative with respect to x of inverse cosine of a function of x that we're calling u is negative u prime over the square root of 1 minus u squared. So these two formulas are only different by a sign. Now, if I'm integrating, again, I want to reverse these formulas. If I'm integrating a function that looks like this, instead of calling it inverse cosine, I'm simply going to call it negative inverse sine. So for that reason, instead of having 6 integral formulas, we're only going to have 3 integral formulas associated with the inverse trig functions. I hope you find that as good news. So this is what we see here in this first integral formula. The integral of du over the square root of a squared minus u squared is equal to inverse sine of u over a plus c. So there's a little bit of the difference in the way that this integrand is presented with respect to the way that we found the derivative. What's the difference? Well, 2 differences. Number 1, instead of the notation u prime, that's now represented as du. That will be some sort of function of x. The second difference is that instead of having a 1 in this position, we now have an a squared. As you saw with some of our derivatives, if you have an argument such as x over 4 in previous examples, and you eventually simplify the complex fraction that results in the derivative formula, you end up with a pattern that looks like this. So this is a very general formula that will apply to those situations. So when we integrate, we have to figure out what the function of x is, what the argument is, and what that constant is. So let's apply this formula to example 4. Find the following antiderivatives. We want to look at the integral of 3 over 4 plus v squared dv. Now the first thing I'm going to do is move the 3 out of the way. It's a constant multiplier, so we can factor it in front of that integral sign. Then we have the pattern 4 plus v squared dv. What triggers your attention on this particular problem is the fact that you have the sum of 2 squares in the denominator. If you have the sum of 2 squares in the denominator, it's very likely going to be related to an inverse tangent, as this one will in fact. So notice in this particular problem, that the u in the original formula is our v. And this a in this position, a squared is 4, so a is 2. So converting this to an antiderivative following this formula, first of all, we have our coefficient of 3 that we have to carry along. Then we're going to have times 1 over a, which is 2, inverse tangent of u, which in this case is v, over a, which is 2, plus c. And that is our antiderivative. As we've discussed many times, you can check an antiderivative finding a derivative. So let's find the derivative with respect to the independent variable v of 3/2 times inverse tangent of v over 2 plus c. So now we're in differentiation mode. We're going to filter that constant coefficient through to the derivative. Then in the denominator, we're going to have 1 plus the argument squared times the derivative of that argument in the numerator. And of course, the derivative of the constant c is 0. So let's make sure this simplifies to give us the original integrand. First of all, let's multiply our 2 coefficients together. 3/2 times 1/2 gives me 1/4. And let's go ahead and square what we have in parentheses here, v squared over 4. Now this is going to be convenient if we multiply this 4 straight across. We would end up with a 3 on the top over 4 plus v squared in the bottom. Notice that matches our original integrand. So we have correctly evaluated the antiderivative. As we move on to the next example, I want to backtrack to our formulas here to draw your attention to something important. Let's compare the first integral formula and the last integral formula. They're very, very similar. Notice with our inverse sine formula, we have a constant squared minus a function of x squared. We've got the difference of two squares beginning with the constant. We also have a difference of two squares under the radical on our inverse secant formula, but this one begins with a function of x and ends with a constant. So to distinguish between these two formulas, make sure you understand a is a constant, u is a function of x. So on example B, notice in the denominator, we have a constant minus a function of x squared. So we'll be using this first formula. So let's identify the specific parts for this example. A squared minus u squared. In this formula, a squared is 36, so a is 6. U squared is negative 4x squared, so we could say u is 2x. Notice again, u squared is 4x squared. Since we're going to make a u substitution here, we need to go ahead and differentiate both sides for an appropriate u substitution. The leftover here in the numerator is dx, so I'm going to go ahead and isolate the dx right here to get 1/2 du. So when we rewrite our integral in terms of u, we're going to have an integral, and I'm going to come back and adjust those limits of integration here in a minute. In the denominator, we have 36, that's a squared, or we'll just call it 6 squared, minus 4x squared, which is u squared, and in the top we have a dx. We're going to replace the dx with 1/2 du. Now, while we're at it, let's go ahead and adjust our limits of integration. Here's the relationship between u and x. If x is 0, u is going to be 2 times 0, still 0. If x is 3/2, u will be 2 times 3/2, or just 3. Now we can integrate directly without having to go back and recover our original variable. So I'm going to move that 1/2 out of the way. The du can either go in the top or the bottom, whichever you prefer. Not the bottom, the top or the side, whichever you prefer. Now, this matches the given formula. So we can look at our given formula and notice the antiderivative is going to be inverse sine of u over a plus c. So applying that to our specific problem, we get 1/2 inverse sine of u over a is 6, and we don't need plus c because we're dealing with a definite integral and we've already updated our limits of integration. So we can now evaluate 1/2 inverse sine of our upper limit. 3 over 6 will reduce to 1/2 minus inverse sine of our lower limit, 0. Remember, when you evaluate an inverse sine or an arc sine, you're looking for an arc or an angle. So we need an angle in the range between negative pi over 2 and pi over 2, where the sine of that angle is 1/2. And we need to evaluate this in radians. Inverse sine of 1/2 is pi over 6, and inverse sine of 0 is 0. So our final result here for the exact value of our definite integral is pi over 12. Let's try another example. See, the integral of 1 over x times the square root of 4x squared minus 25 dx. First of all, notice the order of the difference of two squares under the radical. We're starting with the function of x and finishing with the constant. So we need to identify a and u. Now, this reminds me up here, we need to make a correction. Sorry about this. In our secant formula, we need an absolute value of u out here in the denominator. absolute value goes with derivative. Here's the correct u. Okay, we'll get it right eventually, so there should be a u out there. So u comes first, a comes second. We know this is a secant, so let's identify u and a in our particular problem. So for this problem, u is going to be 2x, the square root of that first term. A is going to be the square root of 25, which is 5. Du then is 2 dx. So let's rewrite our integral now in terms of u. We have 1 over x. Now x, if I solve for x in this formula, x is u over 2, and we have the square root of 4x squared, which we're going to rewrite as u squared, minus a squared, or 5 squared. Now, we do have this dx term left over. We need to isolate dx. Clearly, we can replace that with 1/2 du. So let's go ahead and simplify. Notice right here we have a 1/2 divided by a 1/2 right here. Those are going to cancel, and we end up with 1 over u times the square root of u squared minus 5 squared du, which is our exact inverse secant formula. So inverse secant has 1 over a, that's 1 over 5, times inverse secant of the absolute value of u over a plus c. Again, just following the formula listed in our notes. We do need to go back and pick up our original variable x, so we have 1/5 inverse secant of the absolute value of 2x over 5 plus c as our antiderivative. For good measure, let's check by differentiation. So I'm going to differentiate my antiderivative with respect to x and check and see if it matches the original integrand. So we have constant coefficient 1/5. Now, when we differentiate a secant, if you need to flip back and look at that formula, you can absolutely do that. We're going to have the absolute value of the argument of secant here, that's the absolute value of 2x minus 5 over 5, times the square root of our argument, 2x over 5 squared, minus 1, and in the numerator, we're going to have the derivative of our argument. Again, I'm just following the formula for the derivative of inverse secant. Now, if we multiply our two coefficients together, we have 1/5 times 2/5. I'm going to multiply that out here, call it 2 over 25, and then clean it up just a bit. Absolute value of 2x over 5. Let's go ahead and square this to get 4x squared over 25 minus 1. Now, notice right here, we have 2x over 5, and it's in the denominator. Well, if I'm dividing by a fraction, which is what it being in the denominator means, then I could also multiply by its reciprocal. So this is going to look like 2 over 25 times 5/2 times 1 over x times the square root of all this stuff here. Now let's go ahead and get a common denominator under the radical. We'd end up with 4x squared minus 25 all divided by 25. We can simplify further. Notice here we can cancel our constants. We have 1/5 times 1 over x. Let's split our radical up. In the numerator we have square root of 4x squared minus 25, and in the bottom we have a square root of 25. Almost there. Square root of 25 is 5. Notice we are dividing by 5 there. I'm going to multiply by 5 over 5. It's going to cancel this 5 here. Notice those 5s would also cancel. And there we have our original integrand. 1 over x times the square root of 4x squared minus 25. Matches it exactly. It is a lot of effort to check your work, but first of all, you make sure you have the right answer, and second of all, you get to check, you practice those derivative formulas. Most important thing I can tell you to learn the information in this section as you go through these problems, have your list of derivative formulas nearby and your list of integral formulas nearby. Those are your overarching guidelines. If you can apply those formulas, then you will have mastered this section. Let's try this one, the integral of dx over x plus 2 times the square root of x squared plus 4x. What we can observe about this particular problem is that we have a function of x outside the radical and a function of x inside the radical. This is reminiscent of the formula for our inverse secant. Remember, we've got a function of x out here, make sure you corrected that formula for me, and a function of x here under the radical. So in order for this to work, I need what's under the radical to be the difference of two squares, a function of x squared minus a constant squared. And we don't have that at this point. So what we're going to do is complete the square under that radical in the denominator to see if we can make it match the pattern of our integral formula. So on the top, we have our dx, x plus 2 here, and let's go ahead and complete the square under this radical. Notice the value that completes the square here is 4. Remember, to complete the square, I divide this linear coefficient by 2, that gives me 2, and I square it to get 4. Now, I can't just add 4 under that radical because I feel like it. I got to make sure that it matches the original integral, or it's equivalent to it. So I'm going to add 4 and then immediately subtract it back off so that what I have here is equivalent to that original integral. Now, why would I do that? Well, I now have a perfect square trinomial right here that I can factor. So we have the square root of x plus 2 quantity squared minus 4. Now we have the pattern of a function of x out here that we're going to call u. We've got u squared right here minus a constant squared. In this case, we're looking at a equals 2. So if we make the substitution, u equals x plus 2, then notice there won't be a big change for replacing dx with du. So in terms of u, the integral becomes du over u times the square root of u squared minus 2 squared. So the antiderivative is going to be 1 over a, again, using this formula. Guys, major problems with my formula up here. I'm missing the 1 over a. Please get that in there so that you have the correct formula. The inverse secant has the 1 over a. The inverse tangent has the 1 over a. The inverse sine does not have the 1 over a. So please correct that for me. Glad we caught it here. So we have 1 over a, or 1 over 2, times inverse secant of the absolute value of u over a, which is 2, plus c. So let's go back and get our original variable x. We have 1/2 inverse secant of the absolute value of x plus 2 over 2 plus c. And that is the correct antiderivative. To verify it, you could certainly differentiate it and make sure that it matches your original integrand. And in this case, it would. All right, let's round out this section with a very challenging problem, one that is pretty algebraically intense. Notice we have the integral of x plus 2 over, we have the constant first, the function of x second. So I'm already thinking about the inverse sine function. However, notice we have a mismatch between this value here and this value here. We're going to make those functions match in a similar way that we completed the square above. I want to make both of those spots x minus 1. So instead of x plus 2, I prefer x minus 1. However, I can't just change it because I feel like it. So what I'm going to do is make sure this is equivalent to the original. So I've subtracted 1, I'm going to add it back on, and then put the original 2 there. So right here, I'm adding and subtracting the same thing. That's like adding a 0. So this is definitely equivalent to the original. Now, why in the world would I want to do that? This is going to allow me to split this into 2 different integrals. We're going to rewrite this as the integral of x minus 1 over the square root of 16 minus x minus 1 squared dx plus, and I'm going to zap those 2 numbers together to get 3 over the square root of 16 minus quantity x minus 1 squared dx. Okay, then I can handle these two integrals differently. The first one, we can make a u substitution for the denominator. So I'm going to rewrite this as u equals 16 minus the quantity x minus 1 squared. Then du is going to be the derivative. Derivative of 16 is 0. Derivative here, we're applying our power rule. We're going to get negative 2 times x minus 1 to the first power dx. So now this x minus 1 dx matches what I have right here. As long as I divide both sides by negative 2, we'll have a perfect match. Okay, I can only do one thing at a time, so I'm going to let that second integral hang on a second while I rewrite this first integral in terms of u. So this integral will become the integral of, notice in the bottom we're going to have the square root of u, and in the top we're going to have negative 1/2 du. Okay, that's a very simple integral to evaluate. This is just negative 1/2 times the integral of u to the negative 1/2, du of course. So we can integrate this directly with the power rule. I'm going to add 2 over 2. I'm adding 1 to the numerator. I'm going to divide by that same thing. And then we would end up with negative square root of u. Notice the 1/2 divided by the 1/2 cancels. We have u to the 1/2, which can also be written as the square root of u. So to finish this part of the integral, we're going to replace u with this square root of 16 minus quantity x minus 1 squared. But we still have the task of evaluating this second integral. So let's go back up and complete the problem. We made a u substitution on the first one. Notice here we're going to say that a is the square root of 16 or 4. U is the base of that square, x minus 1. Du then is dx. So in terms of u, this second integral is going to look like 3 times dx, which is du, over the square root of a squared minus u squared. That is our inverse sine function. So we're going to have inverse sine of u divided by a, and now we can get our plus c ready. We can go ahead and replace that u with its original function in x to get 3 inverse sine of x minus 1 over 4 plus c. Now that is a challenging problem. The good news is once you work through this and you understand the overarching pattern of this, next time you run into an integral like this, you don't have to be too creative. You can repeat this process to find the antiderivative. So practice, practice. Make sure you know both the derivative and integral formulas associated with your inverse trig functions.